Welcome to this comprehensive guide on C-sharp design patterns, specifically tailored for beginner developers. In this tutorial, we will demystify complex software design concepts, providing you with foundational knowledge to write cleaner, more efficient, and scalable C-sharp code. Understanding these patterns is a crucial step in becoming a proficient software engineer. Design patterns are essentially proven solutions to common, recurring problems encountered in software design. They offer well-established blueprints, not finished code, that help structure your applications in a flexible, maintainable, and scalable manner. By applying these patterns, you can avoid reinventing the wheel and leverage collective programming wisdom. Throughout this guide, we'll systematically explore three main categories of design patterns: creational, behavioral, and structural. We'll begin our journey by focusing on creational patterns, which are concerned with how objects are instantiated, ensuring a controlled and flexible object creation process. Creational design patterns specifically manage object creation mechanisms, addressing and solving issues that might arise from basic, direct instantiation. They provide ways to create objects in a manner suitable to the situation, preventing design problems or increased complexity that often accompany simple object generation. Our first deep dive into creational patterns introduces the singleton pattern. This fundamental pattern ensures that a class has only one instance throughout the application's lifecycle and provides a single, global point of access to that unique instance. It's about controlling resource usage and ensuring consistency. The singleton pattern proves incredibly useful when your system requires exactly one object to coordinate actions across various components. A prime example is a database connection manager, where having multiple connections could lead to inconsistencies or resource exhaustion. It centralizes control for critical resources. Implementing a robust singleton in C-sharp typically involves several key elements: a private parameterless constructor to prevent external instantiation, a sealed class to prevent inheritance, a private static variable to hold the single instance, and a public static method or property to safely retrieve that instance, often with lazy initialization. A compelling real-world application of the singleton pattern is a load balancer object. In a server farm, where servers may dynamically come online or go offline, a single instance of a load balancer is crucial. This ensures every incoming request is routed through the one object that possesses up-to-date knowledge about the state and availability of the entire web farm. However, it's vital to exercise caution with the singleton pattern. Overuse can introduce tightly coupled global state into your application, making testing difficult and significantly reducing modularity. This can lead to hidden dependencies and make your code harder to maintain and refactor in the long run. Moving on, we next examine the factory pattern, another powerful creational pattern. The factory pattern provides an elegant way to create objects without exposing the complex instantiation logic directly to the client code. It abstracts the creation process, making your code more flexible and decoupled. At its core, the factory pattern defines an interface or an abstract class for creating an object, but it lets subclasses or concrete factory methods decide which specific class to instantiate. This means the client code interacts with a generic factory, unaware of the concrete types being produced. In practice, a factory class encapsulates all the object creation logic. The client code then refers to the newly created object using a common interface or base class, rather than its specific concrete type. This promotes loose coupling and makes it easy to introduce new product types without altering client code. A practical application involves creating different payment providers, such as PayPal or Stripe, based on user input or configuration. Similarly, you could use a factory to produce various vehicle types like cars, bikes, or trucks, where the specific vehicle is determined at runtime, abstracting the creation details from the main application logic. Our third and final creational pattern for this section is the object pool pattern. This pattern is specifically designed to efficiently reuse objects that are particularly expensive to create or initialize. Instead of constantly creating and destroying objects, it manages a pool of ready-to-use instances. The object pool pattern works by maintaining two distinct collections: a list of available objects that are ready for use, and a collection of objects that have already been requested from the pool and are currently in use. This allows for efficient tracking and management of resources. When an object is needed, It's retrieved from the pool's available list rather than being newly instantiated. Once the client is finished with the object, it's returned to the pool, becoming available for future requests. This process significantly optimizes resource usage by reducing the overhead of object creation and garbage collection. This pattern is ideally suited for managing high-resource components such as database connections, threads, or large memory buffers. Creating and tearing down these resources can be very costly in terms of performance, making object pooling an excellent strategy to improve application responsiveness and efficiency. Now, let's transition to behavioral design patterns. These patterns are primarily concerned with algorithms and the assignment of responsibilities between objects. They address how objects interact and communicate, solving problems related to object generation and their integration within a system, ensuring flexible and robust communication. The observer pattern is a cornerstone of behavioral design, defining a crucial one-to-many dependency between objects. When one object, known as the subject, changes its state, all its dependent objects, referred to as observers, are automatically notified and updated. This creates a highly decoupled communication mechanism. In its implementation, the subject maintains a dynamic list of its registered observers. It also provides methods to allow observers to add themselves to or remove themselves from this list. Crucially, whenever the subject's internal state changes, it iterates through its list and notifies all registered observers, triggering their update methods. This pattern is perfectly suited for scenarios like event handling in a graphical user interface, where multiple UI elements might need to react to a single user action. It's also invaluable for tracking dynamic data, such as real-time stock prices, where many displays or components need to reflect the latest market fluctuations instantly. Next up, we explore the command pattern, a powerful behavioral pattern that encapsulates a request as an object. This transformation allows you to treat requests as first-class objects, enabling a wide range of flexible operations that would otherwise be difficult to implement.
By encapsulating requests, the command pattern allows you to parameterize clients with different requests, effectively decoupling the sender from the receiver. It also enables you to queue or log requests for later execution, and crucially, it provides a straightforward mechanism to support undoable operations, enhancing user experience and system robustness.
The implementation typically involves a command interface that declares a single method for executing an action. Concrete command classes then implement this interface, each encapsulating a specific request and its receiver. An invoker class is then responsible for holding and executing these command objects without knowing their specific actions. Consider the practical application of implementing undo/redo functionality in a text editor. Each user action, like typing a character or deleting a word, can be encapsulated as a command object. These commands can then be stored in a history list, allowing them to be easily undone or redone. Similarly, it's excellent for queuing tasks for later, asynchronous execution. The strategy pattern is another key behavioral pattern that defines a family of algorithms, encapsulates each one individually, and makes them interchangeable at runtime. This pattern promotes flexibility by allowing an algorithm to be selected and swapped out dynamically based on context or configuration. A core benefit of the strategy pattern is that it lets the algorithm vary completely independently from the clients that use it. This means you can change the internal implementation of an algorithm or even introduce new algorithms without modifying the client code, leading to highly adaptable and maintainable systems. To implement the strategy pattern, you typically define a strategy interface that declares a common method for all supported algorithms. Concrete strategy classes then implement this interface, each providing a different algorithm. A context class holds a reference to a strategy object and delegates the algorithm execution to it, allowing dynamic switching. This pattern is incredibly useful for scenarios requiring different compression algorithms, where you might switch between zip, gzip, or other methods based on file type or user preference. Another excellent example is integrating various payment gateways, allowing your application to seamlessly switch between providers like PayPal, Stripe, or a custom gateway without altering core business logic. Finally, among our behavioral patterns, we have the state pattern. This pattern allows an object to fundamentally alter its behavior when its internal state changes. From an external perspective, the object will appear to change its class, adapting its responses and actions based on its current condition. The state pattern achieves this by extracting state-specific behaviors into separate, dedicated state classes. The original object, often called the context, then delegates its work to an instance of one of these state classes. As the context's internal state changes, it simply switches to a different state object, thereby changing its behavior dynamically. Consider a classic example, a vending machine. Its behavior drastically changes depending on its current state. It might be in a waiting for coin state, then transition to selection made, dispensing item, or even out of stock. The state pattern elegantly manages these transitions and the associated behaviors, making the code clean and extensible. These creational and behavioral patterns, along with structural patterns we haven't covered in this beginner guide, collectively provide powerful tools for building robust, flexible, and maintainable C# applications. They are fundamental building blocks for complex software systems, promoting good design principles and reducing technical debt. By diligently understanding and consistently applying these design patterns, you can significantly elevate your C# development skills. You'll be able to write cleaner, more efficient, and inherently scalable code, making your applications easier to extend, debug, and collaborate on, ultimately leading to a more successful development career. Thank you for joining this comprehensive tutorial on C# design patterns. We encourage you to not just memorize these patterns, but to actively practice implementing them in your own projects. Experiment with different scenarios and continuously refine your understanding to truly master your C# development skills. Happy coding!